All right, back with the next question. Question 11. Which of the following equations is a consequence of this equation? So, looking at that, not the eraser tool, there we go. We have cross H plus J. So looking at equation A, looks like they take the dot of both sides. But if we end up taking the dot or the gradient of a curl, that is going to drop to 0. So it looks like kind of got lucky, and A is the answer. So that was nice and easy. You just have to remember the rule about gradients and curls. Next question. Let's see. There we go. A source of 1 kilohertz sound is moving straight towards you at a speed of 0.9 times the speed of sound. The frequency you receive is. So that's just a Doppler problem. You have to remember this in a little equation. I have 1 minus V over V sound over 1. Oh, I don't know why I have square brackets, but deal with it. Times the original source. So plug in things in. I have 1 minus, I can just cancel point, I like going through all the steps. 0.9 V sound over V sound. Boom, they cancel. All that under 1 times 1 kilohertz. That's going to give me, all in the brackets is going to cancel down to 1 over 0.1 times a kilohertz. And that is just going to give us the answer of 10 kilohertz. Nice and easy. The vroom vroom car. I don't know if you heard that. My windows are open. Yeah, nice and easy. If you remember the equation, you can just kind of plug and chug. But if you think about it, you can at least eliminate 2 of them pretty quickly. A and B don't make any sense. If it's moving towards you, the frequency is going to go up. C definitely doesn't sound right if it's moving at you that fast, that quickly, 0.9 times. That's pretty quick. So it probably won't only increase by by a tenth. D, maybe. So you're really left with D and E. And if I had to, I would have picked E anyways, just because it's moving basically as fast as it can get to without actually moving the same speed as the wave. So, yeah, process elimination kind of works on that one. Next one. 2 coherent sources of visible monochromatic light form an interference pattern on a screen. If the relative phase of the sources is varied from 0 to 2 pi at a frequency of 500 hertz, which of the following best describes the effect, if any, on the interference pattern? So what they're talking about is let's just say I have a wave there. Pretend these are basically identical. And I'm shifting it 0 to 2 pi, kind of back and forth at 500 hertz. Let's go through the question or the answers, see which one makes more sense. It is unaffected because the frequency, well, you kind of saw there, it's going to be affected. There will be some effect whether you can see it or not. It doesn't matter, but it will be an effect. It is unaffected because the frequency doesn't matter. It is going to be affected. It is destroyed except when the phase difference is 0 or pi. That's not really how interference works. It's going to be constructive, deconstructive, kind of throughout. So we can get rid of that and that as well. So again, process of elimination gives us E, but if you know a little factoid that the limit of the human eye is about 60 hertz, then you can kind of just go down to that one. It is not destroyed, but simply drifts too fast to see. So that is answer for that one. Now moving on to the next question. For an ideal gas, the specific heat at constant pressure, Cp, is greater than the specific heat at constant volume, C sub V, because Let's go through. Gas does work on its environment when its pressure remains constant while its temperature is increased. So let's all draw a little diagram to help us understand. Let's go with CP. So I have some box with a piston, and it's pushed down there. You got my gas doing stuff at that point, and then CV. Same setup, gas doing stuff. If I increase the temperature, so this is going to be T goes up, at constant pressure, the piston is going to move. So it'll be a little higher up here to keep the pressure constant as there's more energy in it now. This one is going to remain the same, so same volume, but now the pressure is higher. So this would be volume going up. This would be pressure going up. So they're asking, why is CP greater? So looking at that, just kind of doing a, not back of the napkin, but kind of. In order to push the piston, work has to be done because it has moved some delta X from its old spot. So there's going to be wasted energy in order to do that work. Not all of the energy is going into increasing the temperature. It's going to go, some of that's going to be wasted pushing the piston away, and that's not going to happen in the constant pressure one. So the specific heat is going to be, and again, this is, I'm not even going to write equals. It's going to be something to do with the heat that's getting input plus that extra work, when this is just going to be somehow related to the heat that's put in. So we can look at that, and that is answer A. But let's talk through this one. This was always a class that made my head hurt. So heat input per degree increase in temperature is the same process for which, or the same in processes for which either pressure or volume is kept the same. So if I have, what is that? So whatever, volume constant, so change in heat per temperature, pressure, that would mean that CV equals CP, but we were flat out told that is not right. So that one is no good. Let's check why the next one might not be right. At the test, you shouldn't be doing this if you're doing this test, but obviously I'm not under a time limit, so I'm just going through and making sure that it's understood why some of the answers aren't correct. Pressure of the gas remains constant when its temperature remains constant. Nope, you can have the volume change. So if the volume changes, then that one doesn't count. Internal increase in the gas's internal energy is greater when the pressure remains constant. And then with the volume, it's not correct. Simple equation here, boom, boom, means that it's only proportional to the temperature. So that one's no good. Heat needed is greater when the volume remains constant than when the pressure remains constant. That's very ambiguous. Heat for what? So if it doesn't tell us what they're asking, we can kind of say no to that. So we got the answer of A. Moving on. A sample of N atoms of helium gas is confined in a 1 cubic meter volume. The probability that none of the helium atoms, or that my brain moved, the probability that none of the helium atoms is in a 1 times 10 to the negative 6 cubic meter volume is, so let's always do a little diagram. Boom, 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 boom. That's going to be your 1 cubic meter, and this is most certainly not to scale, but I've got my truncated 10 to the negative 6 cubic meters. So they're asking, what is the probability that it's not in one of those? So the best way to think about this is to break this down into how many little tiny chunks. So if I've got that many, like 1 cubic meter, and it's split into boxes of that, and not too hard math, there should be 10 to the 6 boxes. So if I want to find out what is the probability that it is in one of those boxes, it is just going to be 1 over that number of boxes. So that will kind of looks like we're going in circles a little bit, but if it wasn't for the numbers the way they are, this would be useful. Then, if we remember, probability of not in or out is going to be 1 minus the probability that it is in. So we have that as our probability for one particle, just a singular particle, being outside of one of those boxes. Now, let's draw a quick line. Now for n parts, you would have to, it's not complicated, but, oh no, I'm out of room. Let me write smaller. So I would have P out 1 minus 10 to the minus 6 to the n. So that would be for every single particle. And if we look, there's our answer. All right. Unfortunately, I think I messed up the border. Yep, messed the border up. Oh well, I'll fix that later. I only got one more question. Except for mass, the properties of the muon most closely resemble the properties of the, this is just definition, it's the electron. The muon is essentially an electron with 200 times the mass. If you know that, you know that. I guess you could maybe go through process of elimination. We don't really know if they exist. Photon really doesn't have much. Again, you would just have to know. Maybe eliminate a photon just because it's kind of its own weird thing. So I guess you'd be able to kind of get it down to a 30%, but even then those are risky. So that's that page.